Hello, this is the 3-axis reaction wheel system for CubeSats Mechanical Engineering Senior Project for the 2020-2021 school year. Our team consists of 4 members, all 4th year mechanical engineering students. From left to right, Rose McCarver, Pablo Casillas, Alex Lee, which is me, and Daniel Leon. Our team advisor is Dr. Andrew Keene from the ME department, and our team sponsor is Dr. John Velardo from Cal Poly CubeSat Labs. Our project goal was to work with Cal Poly CubeSat Labs, or CPCL, to produce low-cost reaction wheels for CubeSats as an alternative to expensive purchased reaction wheels. They must be manufacturable in the Cal Poly machine shops by Cal Poly students, and they must be compatible with a variety of different CubeSat spatial layouts. Finally, our project's goal is to build off an existing master's student thesis on low-cost reaction wheels by Nick Bonifetti. Because we are working off this thesis, the design for the main flywheel and motor was already specified, and our design work will only focus on the housing system. However, the manufacturing, assembly, and testing will focus on the whole system. Our design process started with functional decomposition, where we broke down the main functions of the reaction wheel housing system, then it moved into function concept sketches to illustrate some of our design ideas. Then each team member created functional prototypes using basic materials to get a feel for how these ideas could be implemented. Finally, we created 5 top concept designs that varied between the option of having one assembly or multiple housings for the reaction wheels, and whether or not to contain the flywheel or leave it exposed. We ended up choosing a single housing with an X bracket based on the criteria of affordability, manufacturability, and launch environment.
Moving on to our final design, the assembly consists of an aluminum outer housing, a HIMU 80 housing with an end cap made specifically to shield the internal components of the CubeSat from the magnetic field generated by the Maxon EC10 motor. The assembly also has a stainless steel flywheel, which is the mass moved by the motor to orient the spacecraft, as well as an aluminum X bracket for protection between the flywheel and the internal spacecraft components. The aluminum outer housing has 4 256 tapped holes to interface with the spacecraft structure, as well as 4 wire relief slots for varying orientation. To verify our design before manufacturing, we performed 4 analyses: a quasi-static acceleration analysis for the launch environment, a shaft critical speed analysis, a pure shear bolt analysis, and a hole fit analysis between the motor shaft and the flywheel to compare a clearance fit to an interference fit. We then performed preliminary testing for the hole fit and decided on a clearance fit with epoxy, the reason being that with an interference fit, we ran the risk of bending the shaft.
Moving on to the manufacturing and assembly, the cylindrical parts were made in the CNC lathe with their outer contours and then moved to the CNC mill, and the outer housing was made entirely in the CNC mill. All of these parts have pretty tight tolerances, and the HIMU 80 was a special consideration as it was electromagnetic shielding and had interesting machining properties. The X bracket was water jet.
The next stage of the project was to validate the design. A key test in validating the design was for the wheel to be able to be balanced by a balancing vendor, and this was done by removing small bits of material from the wheel in order to balance the center of mass of the rotor onto the shaft. Additional tests were performed, including a post-balancing max torque simulation, which modeled the wheel post-balancing for the material removal. It determined a new wheel inertia and modeled this wheel in MATLAB and Simulink to simulate the max torque that was provided by the wheel post-balancing, and that met the margins that we desired. An additional test that was performed was a shaft load proof test to test the strength of the epoxy that secures the rotor onto the shaft. An additional test was performed to ensure that the wheel can meet its max acceleration required to ensure the max torque was met. And this is a video of that test.
Here we have a image of our final product next to a quarter for scale. Despite the challenges with all the precise manufacturing, a tough timeline and assembly, we were able to successfully produce 1 out of the 3 reaction wheels and get it balanced and have it perform as expected when reaching above 50,000 RPM. Torque performance was met within 10% of the target and still exceeded that target value. If CPCL can finish procuring the other 2 wheels, get them balanced, and perform TVAC and vibes testing, then the 3 wheels will be flight ready and able to be incorporated into future missions that require more pointing accuracy and 3-axis reaction wheels. With these low cost and manufacturable reaction wheels, with an estimated cost being for 3, $2,500 as opposed to $35,000 each, Lab can save a significant portion of their budget and accommodate these more complex missions that require that pointing accuracy. So we hope that what we've learned from this year can streamline the process and help Lab with future projects that require these reaction wheels. Our acknowledgements go out to CPCL for providing funding, Dr. Bellardo for being an amazing sponsor, and our project advisor, Dr. Keene. And also special thanks to Nick Bonafede for letting us continue his thesis work and build off of that for our project. Thank you for listening.